Okay, so what is the difference between an infinite sequence and an infinite series? Well, an infinite sequence is a list of numbers, a1, comma, a2, comma, a3, comma, a4, comma, dot, 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 going on forever. We have an a5, 6, 7, 8, forever. An infinite sequence is just the list. An infinite series is where we take that list and add them up. a1 plus a2 plus a3 plus a4 plus dot, 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 forever. So your first thought may be, if you're going to keep on adding numbers forever, aren't you going to just get an infinite value? Maybe. Possibly. However, that's not necessarily the case. We will see some instances where, yes, this is going to sum up. We'll have a sum of infinitely many numbers, which gives us basically infinity. And that is what we're going to call divergent. But we're going to see other cases where it's not infinity, but where it might sum up to a finite value. That would be convergent. We'll see other cases still where it doesn't sum to infinity, but it doesn't approach a finite value either. Instead, what it does is it kind of bounces back and forth, maybe like fluctuates around forever and it never settles on anything. That is also called divergent, but in a different sense. Okay, so one way to approach an infinite series is to look at what are called partial sums. So partial sums refer to, instead of adding up all infinitely many numbers of the sequence, what you're going to do is just add the first few. And so we're going to actually create ourselves a new sequence called the sequence of partial sums, and it's going to be denoted by the letter S, capital S usually. So S1 is just equal in value to the first term in whatever sequence you're working with, A1. But S2 is going to be the sum of the first two terms, A1 plus A2. And then S3 is the sum of the first three terms, A1 plus A2 plus A3. So, etc. So that Sn is going to be the sum of the first n terms, A1 plus A2 plus A3, and then keep on going until you get to plus An, whatever you choose n to be equal to. So Sn, this could be written out in sigma notation as the sum k equals 1 to n of ak. That's why, by the way, this is why we're using an n on the top with a k on the bottom. So this is a partial sum of an infinite series. Okay. So now this is going to produce a new series, and when you look at the numbers in this series, you can look at them and look at what they might be approaching. Okay, are those numbers getting bigger, or are those numbers like zeroing in on a specific finite value? Like, are the sequence of partial sums, is it approaching something, like converging upon a number, or is it bouncing around left and right, up and down? Is it getting bigger without bound? That kind of thing. So if Sn, the sequence of partial sums, if this approaches a finite value, which we're going to call L for limit. There's a little bit of calculus concept in here, around limits that where I'm not going to go into detail with. I'm just going to use this arrow to mean like approaches. So if Sn gets closer and closer to a finite value, then this sum k equals 1 to infinity, which is usually represented by S, like the total sum. If you sum up this entire infinite series, that's called S. If that sum exists, that, summing up the AK, is going to equal the L. Whatever number you are getting closer and closer and closer to, converging on, that's the sum of the whole series. Because as you're adding on more and more terms, you're getting closer and closer to the total sum, right? So whatever number you're approaching is the total sum. So in this situation, we can say that the series converges to L or S or L. I don't know. Those are kind of one way or the other. They're the same thing. It converges to this number. If, on the other hand, if Sn does not approach a value, then the series diverges, and S doesn't equal anything because it doesn't have a sum. It could be that it's approaching an infinite sum, or it could be, like I said earlier, that the sum is oscillating back and forth and never really settling on anything. Either way, we say it diverges. So if it diverges, there is no capital S value. There is no L value. That doesn't exist because it's not settling. It's not approaching any particular number. So it's only when it converges that we can calculate the total value of the infinite series, the total sum, as S. Now I want to show you as just a specific example to wrap your head around to help you understand this. Let's go back to this example that I drew a picture for you of earlier. This example here, where we cut this in half and cut this in half and then cut this in half and this 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 and this. This is going to be 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 and so on. So let's write it out here. We're going to have a half plus a fourth plus an eighth plus 1/16 plus 1/32 plus 1/64 and so on. What we're going to do here is I'm going to write down the partial sums, and I'm going to pull up my calculator to help me find the partial sums. Okay, so let's get the calculator in the screen here. I'll put it down here. Okay, so 1/2. The first partial sum, S1, is going to be just 1/2. I'll write it in decimal form here to help us see what's happening. Okay, then S2 is we're going to take the previous answer and we're going to add 1/4. So S2 is going to be 0.75. Okay, that's 1/2 plus 1/4. Then for S3, we can take the previous answer and add. So far, we've got 1/2. Now we've got 1/2 plus a fourth. Now for S3, we're going to do 1/2 plus a fourth plus an eighth. So I'm going to add 1/8. S3 is going to be 0.875. Okay, now let's add the 1/16 to get the next partial sum. So plus 1/16. And we get S4 is equal to 0.9375. Plus 1/32. S5 is going to be 0.96875. Plus 1/64. S6 is going to be 0.984375. And I think you can see what's happening. I'm going to stop writing them down, but I'll add a few more. 64 square doubled is going to be 128. 1/128. 0.992187. Okay, plus 1/256, and we get 0.9960935. Okay, it's getting bigger and bigger and bigger, right? Next is plus 1/1020. What is it? 1024? 1040? No, I can't remember what the next value is. Let's do 256 times 2. Anyway, as you can see, this is getting bigger and bigger. Okay, it's always getting larger because I'm adding a positive number each time, but the positive numbers I'm adding are getting smaller and smaller, right? That's these things getting smaller and smaller, these little triangles. But the overall sum is getting closer and closer and closer to 1. So to put that away, this is approaching the limit of 1. So what that means is that the infinite sum, k equals 1 to infinity, of this sequence, which I'll just represent by AK for now, although we are going to put down an explicit formula for that in the next video. This is summing up to 1. Okay, this is the idea, right? We've got their partial sums, and this produces a sequence that approaches the overall sum, if that overall sum exists. Now, on the other hand, say you want to add up. Let's just take this away for a second and look at the other possibility. Or actually, here I'll just do it on another piece of paper. Say you want to add up 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus forever. Okay, well, you're going to have 1, and then you're going to add 2, then you're going to add 3, and you're going to add 4, and then you're going to add 5 and 6 and 7 and 8 and 9 and 10 and 11 and 12. And the numbers you're seeing here are not approaching anything in particular, right? In fact, they're getting bigger, and the rate at which they get bigger is growing, increasing. They're getting bigger by n every time, right? By or the value of k, right? So this is divergent. This partial sums diverge. So the series is divergent. This is divergent in the infinite sense. The other possible situation is the oscillating. What if you have a sequence, an alternating sequence like 1 plus -1 plus 1 plus -1 plus 1 plus -1, like that. What you're going to get here is you're going to have a S1 equals 1, and then for S2, you'll add up the first two terms and get 1 plus -1 is 0. And then you'll add 1 again and get 1. And then you'll add -1 and get 0. And this is going to keep oscillating between 1 and 0 and 1 and 0 and so on. So this oscillates. And so this infinite oops. Sorry, I'm getting a bit messy here. This infinite series also diverges. Okay, but for different reasons. So this one is diverging because it's approaching infinity, and this one is diverging because it's not approaching infinity, but it's bouncing back and forth, oscillating like this. So that's those are two different types of divergent series behavior that you can have. Okay, that's it.